Okay, so let's start. I will give this playground session on atmospheric phenomena. I'm Marko Blaskovic in the Moodle and forums. So let's start now. In this playground session, I will go through these 6 topics, so dust and dust storm detection, smoke and fire, estimating precipitation, volcanic ash and volcanic SO2 detection, aerosols, and something from identifying areas with clear air turbulence. So let's start from the beginning. You can see here on the right side of this slide an image. I would like you to answer me what can you see, what channel, and what is it useful for? You can write it in the chat box. Maybe some of you would like to say something. You can raise your hand for that. So basically, you see one single channel image. You see some features on it, some clouds on the right side, something on the left side. You can maybe see something in this area around the coast. Can you point something out? You can use your annotation tools maybe to point out something interesting. I'll give you a couple of seconds more. Okay, thank you, Nuno Lopez. Somebody else? Maybe some more similar features. Nuno, can you tell us which channel that would be? You can write it in the chat box. That's true, yes, this is an infrared channel. Do you maybe know which specifically? As you have marked this feature on the image, I assume, or I at least think that you might know what this is. Yes, exactly. The right answer is the 3.9 channel, infrared channel. And here, what you see, what Nuno pointed to, here, and here. These are the hotspots on the Croatian coast and some in Montenegro. This is from last summer, as you can see at the bottom of this image. And what is it useful for? The question below is actually for exactly that, for detecting hotspots, fires, and because it reacts really well to temperature changes and to high temperatures. So it doesn't have a linear change in temperature as the temperature changes, like for instance 10.8, but as the temperature changes, the radiance increases exponentially in this channel. Okay. And later we will again see a lot of this 3.9 channel, and I will tell you later why, and why is it so much used in satellite meteorology. Again, here we can see the same thing, the hotspot that Nuno pointed to. So basically this quite clear signal in the 3.9 channel that is actually used in this night microphysics RGB tells us that this is a hotspot or a fire going on. This is, well, particularly useful in night because this is some additional information, because in the night we have less information from the satellites. We can also see fires here around Zadar and Šibenik in Croatia, here in Bosnia, some here in Serbia and in Montenegro. So because the 3.9 channel is used in night microphysics, the fires are very hot, the signal is very strong in 3.9 channel, and that's why it sticks out so much, comes out so much in this image. The next image is from Portugal and actually Iberian Peninsula. Again, please, could you Could you point to a certain point on the map that seems very peculiar, very different from the others that you see on this image? Can you point out to some specific area? This is also summer, last year, June, night microphysics, so it is in the night. I've seen Nuno pointing to something. It is a cloud. Yes, we see quite clearly the clouds here around. These are some high clouds, not so cold, but high clouds and icy. But what else? Is there one specific thing, a very clear thing in this image, very clear borders? One area, one specific area. I will give you a few more seconds. You cannot point to anything wrong. I mean, this is a playground session. We learn here, so yes, exactly. Ivana, that's correct. That's exactly what I wanted you to point to. So this feature that Ivana is pointing to has very clear borders. You can see the distinction between the a bit brighter purple and this darker purple that you see in this area. And these are again the fires or a hotspot or a burned area that is going on and that can be seen in this night microphysics RGB. And yeah, and here now you can see the explanation for this. So basically, why the color is turning from bright purple to darker purple? So as we probably know, for the purple we need red and blue. And in this picture we have both red and blue. But why is this becoming a more dark purple? Is that this infrared 3.9 signal is getting very strong at this point, and 10.8 has some relatively normal value, but this 3.9 channel is this brightness temperature difference in that case is very low. So there is basically no green or very little green color in this part of the picture, and then the red and blue contributions are high and we get a dark purple color. And here what I was talking about, the reaction of 3.9 channel on changing of temperature. You can see that with linearly changing the temperatures by 20 degrees, you see how the radiance increases exponentially, actually. Here again, we have some smoke fires. In this natural color RGB, which is good for observing snow, smoke, dust over sea, vegetation coverage, and ice clouds. We can again see the same smoke that I showed you just a few slides ago. This is again the same image from the summer, from the last summer, 2017, Croatian coast and Montenegrin coast. We can clearly see the origins of this smoke that is spreading, and even some fires over Italy that are, and the smoke coming from those fires into the Mediterranean. I would like to ask you now, do we use in this RGB 3.9 micrometer channel? You can type in yes or no in the chat box, because we can so clearly see the smoke in this image. So this is basically an indication of fire. Do you think we can? Do you think we use a 3.9 micrometer channel again in this RGB? Okay, we have some answers. Somebody else? One answer for now. I will just give you a few more seconds because we have a lot to cover more. So basically there are no more answers, but the only question was, yes, we use the 3.9 micro channel in this RGB image, but the answer is no, we do not use it. This is a 3.9 micro channel is an infrared channel, and as I explained in some forum exercise that we had, infrared channels do not distinguish sea from the land so clearly, but here we see that the land is clearly distinguished from the sea, and basically we don't see those hotspots that we had before in the 3.9 channel. So the answer is no. We will come back to the recipe for the natural color RGB just in a moment. So as I talked about natural color RGB, it is good for many things, for detecting ice, for detecting smoke, for detecting dust over sea, etc., etc. And in this image, we can also see quite nicely the smoke coming all over from Canada. This is May 2016, the month of those big Canadian forest fires, wildfires that were going on, and the smoke was quite dense, quite the area was quite rich with smoke, and the smoke spread with many systems all to Europe, all the way to Europe. So now I want to ask you one relatively simple question: which color is the smoke? Actually, yeah, I can fill that in for you. Let's say that this is cyan color. Where do we have to put the blue color and the green color for this cyan color? You know that for the cyan color we need the blue and the green color. Red is basically non-existing in the cyan color. Where would you put the blue color? You can mark it with your annotation tools. Take here. Yeah, exactly. That's right, Nuno. And the 0.6 micro. Where would you put the green color? So I assume you probably guessed that this recipe is actually for the natural color RGB. So 0.6, 0.8, and 1.6. And I have to say that Nuno is again correct. So for the cyan color, that is smoke, in the natural color RGB, we have to put 0.6 into blue beam and 0.8 into green beam, which means that the 1.6 is left on the red beam. And what does that actually mean to us? So this is the answer. What does that actually mean to us? That it means that the smoke gets more dense or more optically thick with shorter wavelengths. So you can see here that we have 1.6 micrometer channel. This image, as we go further or down through the wavelengths, we can see 0.8. The difference between the two is visible because in 0.8 we start to see smoke, and in 0.6 the smoke is quite clearly visible as these gray stripes from the coast. So this is an important thing to remember, because the smoke particles are relatively small, and they reflect the solar radiation better from smaller wavelengths. Why is that also important? Because of infrared cameras, for instance, or visible cameras. Depends on from which angle you look. So the visible cameras and visible part of the spectrum are almost all of our cameras. And when the fire is going on, we can clearly see smoke, and behind the smoke, nothing else. The smoke can get very dense, and you cannot know what's actually going on behind it. Is the fire? Where is the fire? Is the fire still going on? How strong is the fire? But in that case, for for detecting actually the source of the smoke, the fire, we can use the infrared cameras. And we can see here that the smoke is rather thin in this image, and that is actually very well described on this previous slides, because the smoke gets more dense with shorter wavelengths, or vice versa, it gets more thin with longer wavelengths. Now I would like to ask you to mark the areas of fires and burned areas. I will give you 10 to 15 seconds just to mark it. You can point it with your pointer or encircle it. Yeah, we see a lot of smoke. Yes, yes. So burned areas and or fires. You can mark both. Okay, I see a lot of smoke. I see some burned areas, some fires. Very well, very well, very well. Good, good, good. Okay, I'm quite satisfied with your answers. A lot of you pointed to smoke, which is actually good. Yeah, because if you track smoke, you can find the source of it. You can find the fire at the beginning of it. I will just erase all your pointers and annotation. I just want to point out now some things. So basically, we can see here red spots in the image, and they are actually fires that can be seen in the natural color RGB. We will come to that just in a second. We can also see burned areas that are brownish, and that comes from the 0.8 channel, because that channel really nicely reacts to the vegetation. So basically here the vegetation is burned, so it reacts in a manner that it shows us where there's no vegetation, and of course smoke, as we talked before. And actually, why do we see these fires, these red spots here, is that in this natural color RGB, 1.6 micrometer channel is used, and this wavelength, this 1.6 micrometer channel, by Wien's law, if you've probably read about it in some of the lectures we provided, by Wien's law, this channel has the most radiation at around 1,800 kelvins, and that is, let's say, 1,500 degrees centigrade, and that's for very strong fires, very hot fires. So for very hot fires, you can even see them as they emit a lot of energy in the natural color RGB. This is also very useful thing in this product. So let's go forward. We'll just change the topic a little bit. I would like to ask you, what do you see here? Actually, yeah, you see a big cloud, that we know that. But why is the cloud so granulated? You can see that it looks like a bunch of rice or sand or something like that. Why is it so granulated? You can write in the chat box, or you can write on the image with the text tool. I've actually posted something similar in the forum last week, I think, where you had to analyze some clouds. And the question was, why was that one specific cloud so special? Anybody? Okay, nobody is answering. Let's go to the next slide. I see a partial answer. Muse, I think you wanted to write something more, but you can still write it, but I will continue with the explanation. So this is basically the same cloud, but from a different angle and in a different not dimension, but from a different area. And we can see that on this cloud's two cutoff lows affect the cloud, and these are the isotext, the geopotential lines on 500 hectopascals. And we can see where the air is coming from into these clouds. So basically this and this cloud. They are getting air from northern Africa. And what do we have in northern Africa? We have a lot of sand. So basically, if we look at the convective storm RGB, which gives us the indication of strong convective systems of Lee clouds, as you can see here, over Carpathian Mountains, and it can give us the information about dust in the clouds. So as we can see here on this image, this would be quite a huge convective system for this time of the year. This was 1st April 2 years ago. That would be quite huge, and with a quite huge convective system with a very strange form. And that's an indication that actually that is not a convective system. So basically, this convective storm RGB also tells us about the content of dust content in the clouds. Especially, it's quite logical to think about that because we're over northern Africa. So yeah, this convective storm RGB, let's go through it once more shortly. In the red color, we have the indication for high clouds. So the red color describes that. The green color describes the particle size and or cloud top temperature. The latter one is not so important at this moment. And the blue color describes are the clouds either water clouds or non-water clouds. And as I said, the bright yellow color and in the image before shows us that there is a lot of dust in the clouds, and the yellow color comes from the red and green contributions. So that means that we have high clouds with small particle size, and that actually means that the dust from Sahara is increasing the number of condensation nuclei and the reflectivity because of that in the infrared 3.9 grows, which brings the green color in perspective, and combined with the red gives us the yellow contribution. If we switch to the dust RGB, the RGB that is mainly that its main intention is to detect dust, we can see that the dust is quite nicely shown here with this pinkish magenta color, and the red color shows us the high, thick ice clouds. The black color shows us the thin ice clouds, etc., etc. But we will now concentrate on this magenta or pinkish clouds. So for magenta or pink, we need both red and blue colors in this RGB. As we can see, the red is this brightness temperature difference, and the blue is the 10.8 infrared channel. So basically, why is red so high? Because you can see on this right image here, because the dust layer transmits more heat through by the 12 micrometer channel than by the 11 or 10.8 micrometer channel. That means that over a dust cloud, this brightness temperature difference is high, so the red color is the blue contribution. I didn't write the time in this image, but it is day, it is light part of the day, it's not night, so everything is basically warm, and there's a high contribution from the blue color also. The green contribution here is not so important because the green contribution is only important for the desert surfaces. You can see that in this lower part of the screen. So basically the 8.7 micrometer channel has a very low emissivity for desert surfaces, and that is why the green is strong in these parts here around where you don't have any dust clouds, only desert soil. So in conclusion, everything together gives us this bright whitish or bluish color. So one exercise for you, just shortly, please mark on the left and on the right image, is day or night, and is the dust that is here and here, is the dust low or high? Please do it now. You have about 10 seconds. Okay, we got some answers for the time of the day. Now you can mark the height of the clouds. Okay, we've got some answers. Some of them are correct, some of them are not. Okay, thank you all together. I would just like to switch to the other slide. You have here the answers. So basically, why is the left image night? As I said before in the slides, the blue contribution, the blue color represents the temperature in this RGB. So more blue means higher temperatures. And this image is quite clearly less blue than this one altogether. If you look at the ground, it is much less blue. That means that the temperature is lower, which means that it is night. Simple as that. Again, for the dust clouds here, they are quite dark. They are purple. They're dark purple. Similar actually to the color of the ground, which means that the temperature is similar, both of the dust cloud and of the ground, which means they're close. And in conclusion, that means that these dust clouds are low. Here, on the other hand, I explained the temperature and the time of day, but the clouds we actually cannot recognize, are they high or low, because during the day there's a big difference between there's a big difference between the top of the clouds, both low and medium, actually all of the dust clouds, low, medium, and high, between them and the ground. So the red contribution is high for all of them. So in conclusion, in combination with the blue color, they all give this bright magenta color. So you cannot know during the day, are they high or low. And this is basically the table you should remember. So during the night, we can detect are the clouds high or low, and during the day, they're basically all of the same color. Another thing, something shortly about forward scattering, that is a quite useful feature in the visible channels and actually in the products that they create. You have heard about forward scattering from Jose in the first playground session. So the main thing is that in the morning hours or in the late afternoon or evening hours when the sun is low, you can see better the dust, especially over the sea, but also here over the land. You can see better than in comparison with the around noon image. You can see that the contrast is quite different. And why is that? Actually, because the sun gives us some photons. The photons reflect on this low angle from the dust cloud, and they flow again to the satellite. So basically that's it. Here they have more direct approach. They pass through the dust cloud. It's more transmittive, and the dust cloud is less visible. Okay, let's go forward to the eruption of Mount Sinabung. You can obviously assume that we are going to the Ash and SO2 part of this presentation. You can see here the eruption. It happened on 19 February 2018 in morning hours European time, but in the afternoon locally. This is a natural color RGB. You can also, with it, as you can see, detect smoke from volcanic eruptions. Not SO2, we will come to that a bit later. But in conclusion, this is a quite useful product for a lot of things. Here we can see some thick ice clouds and some lower water clouds. And this is the impression from that place somewhere near the volcano, and looks quite amazing standing just under it. Let's go ahead to the actual RGBs that are helpful to us in that case. I've put here the dust RGB, which is actually very similar to the ash RGB. They have the same components inside, the same brightness temperature differences inside, and then they can actually see the same things very similarly, as you can see here. Ash RGB would even better see these products of the volcano. So basically in both RGBs you can see ice cloud, you can see the ash cloud, and you can see the SO2 cloud that were coming out of the volcano. So now please just take your annotation tools and please point to the ice cloud first. You know this one, I am sure you know which one is the ice cloud. Okay, yes, we have some ice clouds here on the left. These are normal ice clouds, thick ice clouds from a weather system, normal. But okay, somebody else. So in this area, please. Yes, of course, I forgot to mention. In this area around the volcanic eruption, please point to the ice cloud. Good, good. Now point please to the ash cloud. You can again take these pointers of yours and just move them to the ash part of this gaseous state, let's say. Okay, and point now to the SO2 cloud. Okay, see some movements here. Fine, fine, fine. Okay, we had some interaction. That's fine. Let's continue to the next slide where we will discuss it in a bit more detail. So basically, I would like to show you now. So the ice cloud is this black ice cloud, just like this, like some of you pointed out. It is almost the same, either from a volcanic eruption or from a system or from a weather system. The thin ice cloud, high ice cloud, is almost the same color, black, or really dark at least. The ash cloud is red, here and here. Why is it red? Again, it has high red contribution in this RGB, and the reason is basically almost the same as for the dust. In the dust RGB, we have this brightness temperature difference, which is high because the transmission of radiation is high at 12.0 micrometer channel and low at 10.8 micrometer channel. So basically this difference is high, and so the ash cloud is represented by this reddish color. The green color in this RGB represents us the SO2 cloud, as you can see it here. Why? Again, it is not the same as in the dust RGB. We had there the green color for the desert surfaces, and similar here, the 8.7 micrometer channel, its emissivity, actually the transmittance, lowers quite hard when the radiation is going through an SO2 cloud. You can see that here in this graph. So when the 8.7 lowers, 10.8 is, let's say, the same, the brightness temperature difference is big, and that is why we can see the SO2 cloud and in this greenish color. Another thing I didn't ask of you is this yellowish color. It is not mentioned here, ice, ash, or SO2 cloud. Basically, a yellowish color represents the combination of both ash cloud and SO2 cloud. So basic combinations of colors. Children in school almost know that. So green and red combined give us this yellow color, which means that in this color we have both ash and SO2. Good thing is that not only dust and ash RGB see the SO2 cloud, but also the RGB that we use very often when we are in shifts, at least here in Croatia, because air mass RGB shows us where are the air masses, what are the characteristics of air masses above some certain places. And when you see something like this, this is a quite nice indication that there's a possibility of volcanic eruption around this area, and especially this red color represents the SO2 again. So before we had this green color because of 8.7 micrometer channel, and in this air mass RGB we have this reddish color because of course red contribution from the RGB, and because of this 7.3 micrometer channel, which is even greatly affected by the SO2 that is lowering its transmittivity, which is lowering the transmittivity of radiation through this cloud. So very low and very high, its difference gives us a quite big red contribution. So to compare ash and dust RGB, as I said before, they are really similar. They use the same brightness temperature differences and the same channels. They are only modified just slightly. Ash, of course, for detection of ash and SO2, and dust for detection of dust, as its name says. So you can see here the ash RGB, and here we have the dust RGB. You can see just slight change of color. Actually, the green color is modified, but this is not important at the moment. The most important thing to notice here is that in the dust RGB we have both ice clouds, thick ice clouds, and the ash cloud the same color, while the ash cloud in the ash RGB is quite distinctly red, while the thick ice clouds are more orange. So an exercise now for you, I believe this is now quite straightforward. Please mark where do you see the ash cloud. The ash cloud. Yes, exactly. Most of you are right. So Ivana, as I said, the ash is in the red because the red contribution is the highest in this RGB, and it is very similar to dust RGB. So dust and ash are both visible in the red contribution. So the color of the ash or the dust in the end is more reddish than greenish. Now I'll just clear the pointers. Now please mark the SO2 cloud. Great. Yes, exactly. That's true. Great work. Thank you. And yeah, in the end, we have here a bit of yellow color, and that means that we have some overlapping clouds, ash and SO2. And in this image, we actually don't have any ice clouds, which would be of black color or really dark blue color. Okay, so let's continue. I'd just like to ask you, so you see this 24-hour microphysics RGB. It is summertime, June. It's 5 UTC, so it's morning in Europe. I would like to ask you, in this region on this map, can you please mark the area where you expect afternoon development, so convective storm, convective rain, convection in the end. Yeah, please do not take into account this system. These are fronts and already developed clouds, so please don't take this into account. But everything east of it, please mark something. You can take your marker, highlighter, and encircle an area that you think might have some convective developments in the afternoon. And actually, I have some convective developments right here in Zagreb. I'll just go to close the window. I'll give you some more time. Okay, I'm back. I see none of you actually selected with this highlighter the area that I wanted you to select, but all of you pointed out to some specific places. And actually, yeah, you selected the quite correct places. I'll just go forward to the verification so you can see if you were correct. You can see how the convection spread all over Europe and Turkey. And why is that? Actually, in the 24-hour microphysics, we can see the moisture, lower level moisture, and its boundaries with dry air. So in the next slide, I will do just a short analysis of the same case. We have seen in the slide before, actually, that the blue color is strong, let's say around here, around this area. I've pulled these lines without knowing what will be going on in the afternoon. I ignored the left part of the image because we have more, fronts and systems going on around there. But we can see clearly that there's some kind of boundary here in Central Europe in the blue color. So we see here a pinkish color more, and here more bluish color. It's the same here, more pinkish, more bluish, and some already clouds developing. Here we see very blue colors, and this means that the air is very humid. And in the afternoon, yeah, as we saw, we can see the convection developing on those places where we had this quite bluish color of the ground. Here we can see that the dry air advected in the area, and there was no convection, of course, where the dry air was. Here I missed some places, but here we have some mountains, I think, in Turkey, so it probably also had some orographic influence on the convection. But in the end, in conclusion, 24-hour micro is a very good indicator of moisture, as you can see here, particularly here. You can see the moisture boundary. And especially in the summer times, in the warm part of the years, you can take this product and you can assume that if there will be enough lift, enough instability, that there will be also convective development. One short question for you. So you see, where is it raining, A or B? You can mark it with your pointers. So where is it raining? And since you're so fast on this image, I would like to ask you, how do you know that? You can write the answers in your answers in the chat box. So this is, I will tell you, this is a day microphysics RGB. This maybe helps you regarding the ingredients for this RGB. You maybe know which channels go there, and maybe you can answer why do we see, why do we know actually, sorry, that in B it is raining and in A it is not. Okay, yes, I got one answer from Nuno. Convection clouds. Yes, this looks like little cells. It is quite early in the year, 19th March, so it's probably not some strong convection. Probably some light convection, small cells and light showers. That is true. And here we have some more uniform cloudiness. And it doesn't actually look like some rain. So the answer is actually here. We have some rain, some small showers on the sea, over the sea, and over England we have overcast cloudiness. And actually the answer is for A, not raining because the droplets are too small. Again, in the day micro, we have this famous 3.9 channel that actually shows us where we have bigger reflection, bigger reflectivity from the clouds in comparison with the other ones. So basically the green contribution here is strong. We can all agree on that, because basically the whole cloud is quite green, and that means that the reflectivity is big. This R means that this only the that means that the droplets are small. Only small droplets, small particles give big reflectivity, and from small droplets we cannot have any precipitation. As opposed to here, to B, we have almost none. 3.9 actually going from red to purple. So we have optically thick clouds, and for the purple ones we have warmer clouds, and for the more red ones we have colder clouds. So this is some shallow convection over the sea in early spring, let's say. I see. Okay, no, I hope you will fix your problems with the microphone. We will continue now. Again, Again, for the precipitation, we can use the convective storm RGB that I showed you even before with the dust. Convective storm, as its name says, is clearly meant to be used with convection, and the main signals for strong convection are the yellow signals, as I already mentioned also. So we can clearly see here over the Mediterranean Sea and northern Africa some yellowish signatures in these cells. That means that again, the reflectivity is high in 3.9 channel, so the particles are small, which means that in these strong cells we have strong updrafts. And where we have strong updrafts, that means the cells and the convection going on is really strong. That means that we will get probably a lot of rain, possible hail, and actually in even severe cases, because of the strong updraft, we will get some maybe tornadoes or water or land spouts. Here in the top of the image, we can see some weakening cells. They are more purple or reddish. That means that we have only some high clouds, and the blue means here not watery clouds. So we have some high clouds with big ice particles, as opposed to here where we have small ice particles. And that means that basically the convective cells are falling apart. For the end, I will just mention to you that we have some nowcasting staff products. Actually, we don't have, but the nowcasting staff has. You can check them out on this link. They're quite useful when you don't have radar coverage, or the radar is in process of reparation or is not functioning. So basically, all of these products give you every 15 minutes an estimation and probability, that is the most important part of this, of precipitation. So in the upper pictures, you can see the hourly rainfall accumulation for convective storms. Here is the rainfall intensity of millimeters per hour for convective storms again. And here below you have some probabilities of and likelihoods of precipitating clouds. This is quite useful, as I said, when you don't have radars or the radars are not functioning. But again, very important thing, these are estimations and probabilities. So as you can see here, this is a great area of probable precipitation, but for sure not in all of this area precipitation is going on. So you can check all of the other products on this link up. So let's go forward. Just something shortly about aerosols. During winter, especially over Europe, when we have a stable situation, some parts of Europe, especially for instance here, the Po Valley, tends to accumulate a lot of pollution, a lot of smoke, because it cannot go actually anywhere. We have here Alps, we have here the Apennines, and it can only move to the Adriatic Sea. And in the true color RGB, we can see this pollution quite nicely, and this can be an indicator of problems down the ground, either haze, or maybe we can have smog or fog actually, and actually we can assume that people are not having quite the best time of their lives in this very polluted air. And again, as with smoke and fine dust, we can see it actually in the shorter wavelengths, this true color RGB. It's not important which channels are used, but the visible channels are used. So very small, very short wavelengths are used, and the pollution and the smoke and smog are reacting with the very small particles and are reflected back to the satellite. That's the main intention, main purpose of, well, it's not the main purpose, but it's a very useful thing that we can also use in this true color RGB and actually in the natural color RGB that we will see just in moments. Here again, true color RGB from Aqua Satellite 2012 over USA. We can see a lot of smoke from wildfires that were going on that month. Around 3 million acres, if I'm not wrong, burned down just in August. And of course, this smoke persisted in the area for some time and then shifted probably all around the world with the currents, with the jet streams, and so on. Here in the natural color RGB, we can again see pollution. As I said, very short wavelengths interact with the pollution and the small particles in the smoke. So here in the natural color RGB, 0.6 and 0.8 micrometer channels react, and they give us back this signal so we can see actually this pollution that was going on in New Delhi. And at the end, something recently, this is again natural color RGB. In the recent weeks, we had a non-gradient or nearly non-gradient field over a big part of Europe, southern Europe, and the dust that came here got trapped because it couldn't go anywhere, basically, and it persisted in this area for some time. I think it was a week, maybe even longer. I didn't keep track of that, and you could have seen this dust cloud every morning actually for some days, especially in the morning, as I said before, because of forward scattering and because this cloud was rather thin after some time because it spread over a large area. So in the end, the aerosols can be seen by the true color RGBs, the natural color RGB, and actually all the other possible RGBs that can be created by using short wavelength channels. So let's proceed to the last chapter of this. We will come to the turbulence and actually clear air turbulence. I would like to ask you all to mark the places here on this image where you expect some clear air turbulence. You can mark the areas around in this image so we can discuss that a little bit further on later. Okay. Very nice, very nice. I can see you've read your lectures on the website. So yeah, basically I don't have anything to correct. I would just like to add maybe here something on the left side of the image. It is not so visible, but we will come to the next slide where you will be able to see it better. So basically here we have, here we have jet stream that we will see on the next slide. We can see the red color changing into blue, and that suggests the shift of the change of speeds and the change of air, actually, air masses, and this suggests that there will be some turbulence in the area. Here also we have transverse clouds. So basically the portions of air are moving up, portions of air are moving down, and this creates changes in speed, which results in turbulence. And as you probably know, these transverse clouds are always on the opposite side of the jet stream that is actually here. And I will show you now the next slide. So here, this is the same cloud. as you pointed out, we can expect turbulence here on one part of, on actually one jet stream that is ahead of the warm front, and here behind the cold front. So this is the jet stream, and these are the transverse clouds that are always on the other side of the original jet stream. Some more images about transverse clouds and billows. So you can see here above America, I don't know, yeah, it says here that over northern Missouri, you have huge area of transverse clouds. So this basically means quite turbulent area, possibly turbulent area. And here you can see billows that are manifestation of actually the Kelvin-Helmholtz instability at the lower levels. So this is not that big feature as transverse clouds could be, but also in lower levels it can indicate the possibility of clear air turbulence in the vicinity. Again, one example, a split front, when we have different air masses going on, and if we are going through them actually, we can expect turbulent environment. So basically here where we see on this water vapor image, the dry air is subsiding from higher levels from tropopause or stratosphere, and here again, and here again, here we can see double fronts, actually split fronts, and basically as you have this subsiding, actually descending air and ascending air coming one after the other, you can expect quite turbulent environment because of all this speed changes, velocity changes. Something more about Lee waves. You can see nice example of Lee waves here of the Dinarids in Croatia under the influence of the Bora effect. This is quite nicely now seen. Bora can sometimes blow in really clear weather, so you don't have anything here, but in this example you can see really nice Lee clouds over Dinarids, and yes, flying through this is not at all comfortable. I've flown once through the Bora from Split from here, and I can say it's quite a show. It's like being on a roller coaster. You're going up and down all the time. But then we had, I think it was quite clear skies. It was an anticyclonic Bora event. And actually, yeah, that was clear air turbulence, as the name actually says. Now, for the end, some more pictures. Please, again, just annotate where you expect some turbulence in this image. Yes, fine. Somebody else, yeah. So basically the changes of color, especially from red, are quite turbulent because the red symbolizes dry air coming down from tropopause and actually indicates the presence of jet stream. So basically wherever we have jet stream, we have a lot of velocity changes, actually then acceleration, which then brings us to turbulence in the end. So we can see here this jet stream change of color from bluish to reddish indicates the possibility of clear air turbulence. And here we actually don't have any clouds in this area, and that would be a really nice example of clear air turbulence if we would fly through that. And here we have some frontal cloudiness. Of course, here we expect also some turbulence, not so hard maybe as like this, but basically any frontal cloudiness, if you go through it, you can expect some turbulence. At the end, I would just like to ask you to annotate, to encircle, or to point out to jet fibers that are on this image. There are several jet fibers visible. Some are not so obvious, but when you see the overlapping image with the isotext, you can quite clearly know that they are there. So please just point out to some jet fibers if you can see some. Okay, some answers. Okay, yeah. Okay, I see it. Now the colors are really similar to the pencil that you are using, so I didn't immediately recognize it. But okay, the answers are quite fine. I will proceed to the next slide. So basically here you can see where the jet streams are. So here we can see quite nice example. Sorry, I'll just remove. We can see the color. Let me change the color. Here we can see nice jet fibers here on this cloud. Here some clouds, jet fibers, and possibly here on the left side, and probably also in some other places, but they are not so well distinguished in this image because we are looking actually for dark cirrus formations on the edge of the red cloudiness and in the vicinity of jet streams. So basically these are all the very visible jet fibers that we can see on this image. And yeah, that would be all from me. Thank you for bearing with me all this time. I believe you're tired after 1 hour of this, but that would be all from me. Thank you for your attention. And now if you have any questions, please, you may ask. Thank you again.